Hi, everybody. Mr. Wiggins here. In today's episode, we're going to look at two of the most abstract ideas, I think, in the forces and field unit, and that is electrical potential energy compared to electrical potential difference. We'll start with electrical potential energy because we can kind of refer back to it or refer back to potential energy when we're thinking about electrical potential energy. So when we're talking about electrical potential energy, we want to be able to describe it, and B, we're going to use some equations like usual in physics to solve some problems. So first, let's look at how we're going to relate some of our kinematics and dynamics equations to electrical potential energy. So if you remember, we defined work back in physics 20 as force times the difference in distance. Well, we're going to relate that to electrical force. So we're going to say the work done by electric force is the change in distance. So if we move our charge here from A to B, that's our delta D, just like before. And some electrical force was required to do that. And the multiplication of those is going to be your work. All right, so the electrical potential energy is kind of the energy that it would take. So if you remember back to physics 20, when we talked about just potential energy, we usually talked about it when we had something on a surface and it was going to move down. Or if we move something from the ground onto the desk, we increase the potential energy it had. And if we drop something from the air, we decrease the potential energy because it changed to kinetic energy. Well, it's very similar here with electrical potential energy, except instead of just talking about like up and down, we're talking about any direction, because if you apply electrical force to some kind of charge, we can move it in any direction. So here we're talking about the energy stored in a system due to a change in electric field. So basically how much energy could be provided by an electric field. And again, this electrical potential energy can be changed into kinetic energy and heat energy and all those sorts of things. All right, so quick math here. We're going to say just kind of like in kinematics, except here for electrical potential energy, it's the negative of the work. And we already said that work is the force of the electric times the distance. And then if you remember back, this force electric is also equal to the charge times the electrical intensity. So here's just a quick equation for electrical potential energy of an object. And again, we'll summarize it. So if you forgot, we're going to say that our EE here is the electrical potential energy of a field, and we're, like all energies, we're going to measure it in joules. We have Q, as previously. Q is going to stay the charge of the object in coulombs always. Epsilon as the electric field intensity, and it's in newtons per coulomb. D is the displacement of the object, and it's important to remember it's in meters. Sometimes we're going to be using very, very small numbers, but remember to change those to meters first. Okay, so we just finished talking about electrical potential energy. Now we're going to talk about what electrical potential difference is. All right, folks, so we just talked about what electrical potential energy is, and now we're going to talk about what electrical potential difference is. And there's actually a big difference between electrical potential energy and electrical potential difference. I'm not sure why they gave them such a similar name. We do use electrical potential energy to find electrical potential difference, but they are not the same thing at all. So I'll do my best to give you a good idea of how to compare them. So after we talked about electrical potential difference, I really want you to understand the difference between the two of them, and then also we'll look at a problem in 2 dimensions, since the one-dimensional problems are reasonably simple, and you can check the full slides for them. So we talked about electrical potential energy, but if we're just talking about electrical potential, and it is a different thing than electrical potential energy. Sometimes electrical potential is referred to as electrical potential V. But what that is a measure of electrical potential energy per charge. And you'll notice when we talk about the units in a second, it's probably in a very familiar unit that you might not have understood before. So we look at it, we denote electrical potential by this big V, and it is the electrical potential energy over the charge, and big V is volts. If we look here, we see that volts is equal to joules per coulomb. That's the way I like to think about it. If you want, you can also look at it's newtons meters per coulomb, but I find it easier to think about this in joules per coulomb. So energy per charge. Skip this. Okay, the other way that we can use this electrical potential is an electrical potential difference. And thankfully, electrical potential difference is sort of self-explanatory in the sense that we're just measuring the change in delta V, or measuring the change in V, so delta V. So if we have VB minus VA, we get this delta E, so delta electrical energy over charge, because our charge in these cases aren't changing, so this is just the change in electrical potential per charge. And we can use different tools such as a voltmeter to measure this. We can also calculate it, so we'll look at an example in a second of how to calculate it and why it's useful. It's useful because we can measure like how electrons move and measure the amount of potential energy things have. Okay, so electrical potential difference, if we want to talk about delta V, is the amount of work required per unit of charge to move a positive charge from one point to the other in the presence of electric field. That's pretty much the words that are here. And if we look at this diagram, all that's saying is the amount of energy per charge that's required to move this charge from here to here. So it's useful because if this charge changes, we can figure out how much energy is required to move any charge, as opposed to just if it was just one proton. To move the one proton this distance, or to move 100 protons this distance, we can figure out from the electrical potential difference. And then just talking through some math, because I know that's usually useful. We have this equation here, which is delta, or so our electrical potential charge, or sorry. So if we just want to look at some math, a little bit of a derivation, we can talk about how our electrical potential difference is equal to our electrical potential energy over charge. And we know that electrical potential energy is equal to negative of the work. And if we expand a work out here, we get minus charge times the electrical intensity times the displacement over the charge. So these two charges cancel out. And so we just get the electrical potential difference equals the negative of the electrical intensity times the displacement of the charge. So again, just summed up here with all the different variables listed. So here we're just rearranging the equation to show that if we want to look at a uniform electric field, because it stays the same, that our difference in charge change blah, 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 blah. So if we look at this slide, and this is just the electrical potential difference rearranged, so that we see the intensity, we notice that the okay. So if we rearrange this equation, we can see that the electric field intensity will change, even though this is a uniform field, based on the position of the charge and also the electrical potential difference. And that's just the only reason why we rearranged it, was to show that the electrical intensity, field intensity, will change based on just the electrical potential and the distance. So if we think back to that equation and the other equations in the past, we can kind of sum up the following about the electric field. So about epsilon, it's greatest where the electrical potential difference is greatest. It changes rapidly based on small changes in displacement because it is the denominator in the question. It's 0 in regions where electrical potential is constant, because if electrical potential is constant, then the difference is constant and we get a 0 in the numerator. And then it points from regions of high potential to regions of low potential. And that becomes important in an example we'll do, where we think about what's happening before we try to start solving the example. Okay, so this is where electrical potential becomes a little bit tricky, or can become confusing. So if we think about potential differences, so we're thinking about a high charge and a low charge. We're thinking about both positive charges. A positive chest charge, which is something we've talked about a lot in the past, will move from a high potential, so from a very positive source, to a less positive or negative source. But when we talk about electricity, we're talking about the flow of electrons. So what we have to remember is that electrons move from low potential to high potential places, where we're talking about from lower positive areas to higher positive areas. And I think that makes sense when you think about electricity being electron flow. So electrons are going to flow to more positive areas because they're negative. And here's an example. So before we look at the solution to this example, let's just think about what's happening. So here we have an electron, and it's moving through these parallel plates. And just by thinking about it before we like talk about numbers or anything like that, we see an arrow here, so we know it's moving through the parallel plates. We know this top is positive. We know the bottom is negative. So if we just think about this, the electron is going to be attracted to the positive and repelled by the negative. If it ends up leaving the parallel plates, it's going to have also an upward velocity. Right now, it's only got a horizontal velocity, but at the end, it will also have an upwards velocity caused by this positive plate and negative plates, caused by the field, which is pointing down. So the electron is moving in the opposite direction to these arrows, and that was what the previous we talked about just previously. So let's look at the numbers now, and we'll solve this here together. I think this is probably the most difficult problem in this section, and it takes into account some physics 20 material as well as physics 30 material. So we have an electron. This is always the charge of an electron 1.6, moves horizontally with a speed of 1.6 times 10 to the 6 meters per second between two horizontal parallel plates in the diagram. These plates have a length of 12.5 centimeters, so that distance is 12 centimeters. And this side allows the particle to escape, so it does escape. The magnitude of the electric field within the plates is 150 newtons per coulomb. And again, we can remember that it is uniform throughout the plates here. So what the question is asking us to do is to calculate the final velocity of an electron as it leaves the plate. So bear with me, I have solved the entire problem in the next slide just to save some time, and we'll work through the answer step by step together. So up here I've written what we know. So we know the charge, we know the electric field intensity, we know the initial velocity, we know delta D is 0.125 meters. We know what the mass of electron is. It's not given in the question, but it's just a constant in the universe, so I wrote down that. And the reason I wrote it down is because we're talking about energy and speed. It's sometimes just good to have the mass there, because in previous problems, as you might realize, we used kinetic energy, and it's going to become important in this question. And what we're trying to find is the final velocity. So first thing we want to do is figure out how much energy, because here you'll see that the initial energy is always equal to the final energy, right? But we want to know how much energy the electron, potential energy the electron has is before it starts moving, or when it first enters the parallel plates. So we're going to use this equation, the electrical potential energy over the charge is negative to the work, or epsilon d. So rearranging that equation, subbing in for that equation, solving that equation, we get that there is 3 times 10 to the minus 18 joules of potential energy there. And that is only, remember, it's opposite to the force, so that energy is in the up direction. And that is why here I have this X and Y table I made, and we'll come back to that in a second. So our initial energy in the Y is all potential electric energy. There's no kinetic energy. It's not moving at all at the beginning. But at the end, it leaves the field, so there's zero electrical potential energy, and all that potential energy has been changed to kinetic energy. So we can say that 3 times 10 to the 18 joules equals 1/2 mv squared. We solve for V, we get 2.56 times 10 to the 6 meters per second. So here you'll see I've subbed that into my table up here just to stay organized. Our initial velocity in the Y direction was 0, and then the final is 2.56 meters per second. Then I made a little vector diagram here to show what's happening. Our horizontal speed hasn't changed at all, 1.6 times 10 to the 6, 2.6 times 10 to the 6. If you use Pythagorean theorem, like we've done so much in the past, you get 3.0 times 10 to the 6. And then we also need to find this angle. It is 57.99 or 58. So our final velocity is 3.0 times 10 to the 6 meters per second. And then depending on how you want to write the direction, you can either write it as, say, you could write it as east 58 degrees north. You could write it as right 58 degrees up. You could write it as north 32 degrees east. As long as you remember, again, as long as you define your coordinates, I'm okay, and anyone should be okay with the way you want to write it. just some people have specific ways that they like writing it. I hope that that clears up some of the questions people have had about electrical potential and electrical potential difference. I do think that energy versus difference is one of the most confusing things in the unit to understand. And again, I hope that this video is helpful. Please leave me some feedback in the comments. Looking at adding, like I said in the previous video, in future videos. All right, thanks for watching.